Hello and welcome to the session. In this session, we are going to discuss the following question, and the question says that examine the function for relative extrema z is equal to minus x square minus 5y square plus 10x minus 10y minus 28. We have already discussed in this chapter the second partial derivative test for finding relative maxima and minima, which says that let f be a continuous function having second partial derivatives on an open region R containing point AB for which f sub x at AB is equal to 0 and f sub y at AB is equal to 0. To find relative extrema of f, consider the equation d equal to f sub double x at AB into f sub double y at AB minus f sub xy at AB whole square if d is greater than 0 and f sub double x at AB is greater than 0, then f has a relative minimum at AB. Also, if d is greater than 0 and f sub double x at AB is less than 0, then f has a relative maximum at AB. But if d is less than 0, then f at AB is a saddle point which is neither relative maximum nor relative minimum, and the test is inconclusive if d is equal to 0. With this key idea, let us proceed with the solution. We have to find the relative extrema of z equal to minus x square minus 5y square plus 10x minus 10y minus 28. Let us first find its partial derivatives. We have f sub x will be equal to minus 2x plus 10, as we have to keep y constant for finding the partial derivative of z with respect to x, and f sub y will be equal to minus 10y minus 10, as here we keep x constant while finding the partial derivative of z with respect to y. So they exist for all xy. This implies that critical points exist. Now let us find the critical points. For this, we put both partial derivatives equal to 0 and evaluate for x and y. So we have minus 2x plus 10 is equal to 0 and minus 10y minus 10 is equal to 0. This implies minus 2x is equal to minus 10, which implies x is equal to 5 and minus 10y is equal to 10, which implies y is equal to minus 1. So, AB is equal to 5 minus 1, is a critical point and is the only critical point. Now we form the equation D equal to f sub double x at AB into f sub double y at AB minus f sub xy at AB whole square. Now since f sub x is equal to minus 2x plus 10, now differentiating again partially with respect to x, treating y as constant, we get f sub double x will be equal to minus 2. Also, as f sub y is equal to minus 10y minus 10, differentiating it again partially with respect to y, treating x as constant, we get f sub double y equal to minus 10. Now, to find f sub xy, we differentiate f partially with respect to x and then with respect to y. So we have f sub x is equal to minus 2x plus 10, and on differentiating this partially with respect to y, keeping x as constant, we get f sub xy will be equal to 0. So now f sub double x at 5 minus 1 is equal to minus 2, f sub double y at 5 minus 1 is equal to minus 10, and f sub xy at 5 minus 1 is equal to 0. Now we have to put these values in the equation D equal to f sub double x at AB into f sub double y at AB minus f sub xy at AB whole square, which implies D is equal to f sub double x at 5 minus 1 into f sub double y at 5 minus 1 minus f sub xy at 5 minus 1 whole square is equal to minus 2 into minus 10 minus 0 whole square, which is equal to 20. So, D is equal to 20, which is greater than 0. Also, f sub double x at 5 minus 1 is equal to minus 2, which is less than 0. From the key idea, we know that if D is greater than 0 and f sub double x at AB is less than 0, then f has a relative maximum at AB. So here the given surface has relative maximum at 5 minus 1. Now z is equal to minus x square minus 5y square plus 10x minus 10y minus 28 at x equal to 5 and y equal to minus 1. We have z is equal to minus 25 minus 5 plus 50 plus 10 minus 28 equal to 2. So, the relative maximum point is 5 minus 1, 2. This is the required answer. This completes our session. Hope you enjoyed the session.